Hello everybody, my name is Iman Asadi. Welcome back to my YouTube channel. Today we're going to cover the latter half of chapter 14. Now, today we're going to cover mass spectrometry. We have talked about infrared spectroscopy in the last video, and so today it's time for mass spectrometry. Now, again, to start this discussion off, let's define one more time the difference between spectroscopy and spectrometry. Now, spectroscopy is the science of studying, right, the interaction between matter and energy, while spectrometry is the method used to acquire a quantitative and numerical measurement of the spectrum. Spectroscopy does not generate any results. It's simply observing the interaction between matter and energy. It's a theoretical approach like we said last time. Spectrometry is the practical application of spectroscopy where results are actually generated. Now, keep this in mind and let's start talking about mass spectrometry. Now, when you're in a lab and you have formed a chemical substance that you need to identify, what do you do? Well, we talked about how IR spectroscopy does a great job of giving us information about functional groups. Well, mass spectrometry, as you'll soon find out, gives us great information about the mass and the molecular formula of a molecule. And we'll cover this in chapter 15, but NMR is another useful instrument that we can use in addition to IR and mass spec to really gain more information about an unknown molecule, because it's going to give us the carbon and hydrogen environment of our molecule. And a lot of scientists use all these instruments together to get a lot of useful information about molecules that they're trying to identify. Awesome. Now, mass spectrometry is the study of the interaction between matter and an energy source other than electromagnetic radiation. And it's used to determine, like we said, molecular weight and formula of a compound. But how does it work? That's a great question, guys. Now, in a mass spectrometer, a compound, all right, you enter your sample molecule or your compound, and it's going to be first vaporized and converted into ions, which are then going to be separated and detected. Now, the most common ionization technique, right, to ionize our molecule or compound involves bombarding the compound with these high energy electrons. What happens when a high energy electron strikes the molecule? Well, it causes one of the electrons in the whole molecule to kind of be ejected, thrown out. All right. This technique generates this high energy intermediate that is both a radical and a cation. All right, so if you have a starting compound that you bombard with high energy electrons, you're going to have one electron from this compound being ejected, and what you get is this radical cation. It's a radical because now it has an unpaired electron, and it's a cation obviously because it bears a positive charge as a result of losing that electron. The mass of that electron we lost is pretty much negligible compared to the mass of the whole molecule, so the mass of this radical cation is essentially pretty much equivalent to the mass of the original molecule before it lost a single electron. All right, this radical cation is called the molecular or the parent ion. All right, and it's usually assigned this sort of symbol, all right, M plus dot, right, for cation and unpaired electron. All right, you will see it commonly referred to as this, or molecular ion, or parent ion. All of those mean the same thing and are referring to this radical cation. Now, this radical cation, this molecular ion, is very unstable. And what's going to happen to it is that it's going to fragment. All right, and it's going to generate two distinct kind of fragments. All right, one fragment is going to carry the unpaired electron. All right, and that's called a radical. And the other kind of fragment is going to carry a charge. all right, it's going to be referred to as a carbocation. Now, in this way, the ionization process is actually going to generate many different cations. The molecular ion is one that you're going to observe in the mass spectra at the end, as well as all the different carbocation fragments that can form from the molecular ion. And all of these ions are going to be accelerated through, and then sent through a magnetic field and then deflected in different paths, and then at the end observed in the detector. All right, so essentially the molecule of interest or the compound of interest is vaporized and turned into an ion because an electron is going to pretty much get kicked out or ejected. All right, only the molecular ion, all right, and all its cationic fragments are deflected. All right, and these cations are separated by their mass to charge, which is just effectively a measure of just the mass, because each cation will only have a charge of 1. And a plot at the end is generated. Called the mass spectrum. And it's going to show the relative abundance of each cation that was deflected at the end. Your tallest peak here is your base peak, and sometimes your base peak is your molecular ion. Sometimes it's not. All right, so just one more time to summarize. All right, the goal is to understand that mass spectrometry is a form of analyte identification, all right, through molecular mass. How do we do this? Well, we pass a molecule through the instrument, the mass spectrometer, all right, that will ionize and fragment your molecule into pieces that are gonna be eventually detected. All right, and as a result, you will get a spectra of the molecules' masses that you observe, and you're going to identify signatures from them. So, for example, look at this molecule. It's a methane. It's going to go through the mass spectrometer, all right, and it's going to get one electron is going to be ejected. So instead of having a bond right here between this carbon and hydrogen, well, one electron will be ejected, and you'll just have one electron between one of the carbon and hydrogen bonds. All right, this is that radical cation. This is your molecular ion. And remember, this radical cation will have the same weight, molecular weight, as your original molecule, because all you lost was a single electron. All right, same molecular weight as your molecular ion. All right, the weight of methane is 16, which is, guess what, why you see this peak at 16. All right, this refers to your molecular ion. All right, it's at 16. Now, if this molecule lost a hydrogen in the process of fragmentation, then you'll just have a CH3+. All right, when you lose one hydrogen, a hydrogen has a molecular weight of just 1. All right, if it loses just one hydrogen, then its molecular weight will now be 15, which is why you see that fragment. All right. All right, so this is CH4+. This is if it lost one hydrogen, CH3+. What if it loses one more hydrogen? All right, if it lost one more hydrogen afterwards, all right, so then it's only CH2. All right, that molecular weight will be 14. What about just CH+, right? If it only has one hydrogen, all right, that's going to be a molecular weight of 13. And then if it's just the carbon, all right, that's at 12. All right, so the potential of this methane to fragment in many different ways can and will happen when it gets passed through the mass spectra, and you're going to see every possible fragmentation in your mass spectra. Now, sometimes it's kind of hard to see it this way and think of it as a molecule being fragmented. So I want to show you an example, and this really helped me learn mass spectra when I was learning. All right, let's take a molecule, and our molecule is going to be the word bat, for example, okay? Now, bat, this molecule bat, for example, has a molecular weight, all right, a total molecular weight of 45. Okay, the B has a molecular weight of 10, all right, the A of 15, and the T 20. All right, now BAT can fragment into B, into A, into T, but it can also fragment as BA, for example, and that would have a molecular weight total of 25, right? 10 plus 15. It can also fragment as AT, and that would have a total molecular weight of 35 because 15 plus 20. All right, so you pass this molecule back through your instrument and it's going to ionize and fragment maybe into B, maybe into A, maybe into T. Those are all possible fragments. BA is another possible fragment. AT is another possible fragment. And what you get is after you've run your sample molecule BAT, all right, and it has been ionized, all right, and you get, this radical cation, and it'll fragment into your possible B cation, your possible A cation, your possible T cation. These are all potential fragments. You might get your AT cation as a fragment from your original molecule. You might get BA as a potential fragment, all right? And essentially your instrument, all right, will order all these fragments, all right, from smallest molecular weight to larger and larger and larger molecular weights in that order. And then it will go through your detector. And as a result, you'll get this mass spectra, all right, where your molecular ion, all right, your M plus dot is going to be at 45 because that's the total weight of your molecular ion. But then you'll see a peak at 35 for your AT fragment. You'll see a peak at 25 for your BA fragment. You'll see a peak at 20 just for your T fragment, and then your A fragment, 15 for your A fragment, and then at 10 for your B fragment. Right, so if you think of it as a word, your molecule as a word, and you have potential fragments that can come from that, all right, this is an interesting way of thinking of it, all right? If you have your BAT molecule, all the possible fragments you can get, all right, and then they're ordered in terms of your mass and detected, and you get this spectra as a consequence. All right, so this really helped me think of mass spectrometry in a slightly easier way because it's kind of hard to think of it straight up as a molecule and all the potential ways it can fragment. All right, now there are some things in mass spectra that require your attention and you should keep in mind. All right, so I'm going to talk about these few points. All right, and these few points will make a lot more sense when we jump into the practice problem set for these right away. All right, so we're going to talk through these and then we're going to do some practice problems. All right, so for some compounds, the molecular ion peak is the base peak. All right. That means it's going to be the peak that your largest peak. A base peak is your largest peak, and sometimes your molecular ion peak is going to be your base peak, and sometimes that is not the case. All right. When analyzing your mass spectra, the first step is to look for your molecular ion peak because it's going to indicate to you the molecular weight of the molecule, and that is going to help you distinguish compounds. Most of the time, you're going to be told which peak is your molecular or parent ion. All right. Now, useful information that can also be obtained by analyzing whether the molecular weight of another useful information is analyzing whether your molecular weight of your parent ion is odd or even. All right, because an odd molecular weight is going to indicate an odd number of nitrogen atoms in your compound, while an even molecular weight is going to indicate either the absence of a nitrogen atom or an even number of nitrogen atoms, and this is called the nitrogen rule. So that's important to know. All right. Usually, whenever you have an odd number for your molecular weight, you can assume that you have an odd number of nitrogen atoms. Now, sometimes you're going to observe a M+1 peak. And this is a consequence of the possibility of having isotopes in your sample. Now remember, when you run a mass spectra of a compound, take methane for example, all right, you're taking methane and you're running it through your mass spectrometer, all right, you're not just running one methane molecule through your mass spectra. No, okay, you're never running just one of your molecules or compounds. You're running a certain amount, all right, say 1 mole of your compound or molecule, all right. So if you take methane and you're running it through your mass spectra, you're potentially running, say, 1 mole or more of methane through your mass spectra. Some of those methanes, all right, all right, are going to have your normal 12 carbon, all right, your normal form of carbon. Some of your methanes are going to have the carbon atom be an isotope, so carbon 13 instead of carbon 12, all right? That is really important because if you have some 13 carbon 13 in your molecules, all right, your carbon isotope is going to be seen as a M+1 peak. All right. Now, it's important to note that carbon 13 is the second most abundant isotope of carbon. All right. And it's going to constitute approximately 1.1% of all the carbon atoms. So if you're running a certain amount of methane through your mass spectrometer, all right, about 1.1% of the carbons that are present in that 1 mole of methane will probably be in the form of carbon 13. All right. And that means it is generally possible to determine the number of carbon atoms in an unknown compound simply by comparing the relative heights of your molecular ion and your M+1 peaks. And we're going to see this in a few practice problems. Now, some molecules are going to actually have a dominant isotope that are 2 units apart. So then, in that case, sometimes you're going to observe M+2 peaks. All right, 2 elements that you're going to see give this characteristic peak are chlorine and bromine. So near the end of your mass spectra at the higher weights, compounds that contain a chlorine atom are going to give a characteristically strong M+2 peak, where the peak at M+2 is going to be 1/3 of the height of the parent peak. All right, and then you're going to see molecules that contain bromine. They're going to have the same signature, except the peak at M+2 is approximately the same height as your parent peak. All right, so let's do a couple practice problems to really put all of these rules into play, and it'll make it so much more easy to understand what all of this means. All right, so let's go ahead and jump into our first practice problem. All right, this first practice problem says, how would you distinguish between each pair of compounds using mass spectrometry? All right, so at A, you have this molecule and this molecule. How are you going to distinguish between the two using mass spectrometry? Well, this first molecule is called furan, all right, and it's going to have a molecular weight equal to 68. All right, this molecule right here is called cyclopentadiene, all right, and it's going to have a molecular weight of 66. So the way that you're going to distinguish between each pair here, between this pair, is that the molecular ion peaks are going to be different in each mass spectra. So you're going to have your molecular ion peak for furan at 68, and you're going to have your molecular ion peak for cyclopentadiene at 66. So that's one really good way to distinguish between this pair in a mass spectra. Now, for this pair, all right, this molecule, let me do a different color. This molecule is called benzene, all right, and it's going to have a molecular weight of 78, all right, and this is called pyridine, and it's going to have a molecular weight of 79. All right, so the way to distinguish between the two is by their molecular ion peaks. Benzene's going to have its molecular ion peak at 78, where pyridine will have its molecular ion peak at 79. Fantastic. Now, let's do this problem. This problem says, propose a molecular formula, all right? Now, it says propose because you could potentially get two different answers, and that's okay. Propose a molecular formula for a compound that exhibits the following peaks in its mass spectra. All right, so for A, it says your molecular ion peak is at 72, all right, and its relative height is 38.3% of the base peak. So your molecular ion is not the base peak here. That's okay. All right, and then you're going to have an M+1 peak. It's going to be at 73, and its relative height to the base peak is 1.7%. Now, in order to determine the number of carbon atoms, for this, we're going to have to compare the relative heights of our molecular ion peak to our M+1 peak. All right, so all we have to do to determine the number of carbon atoms in our molecule is first, we're going to divide 1.7% by 38.3% and then multiply that by 100%. All right, if we do this, what we get is 4.4%. Now remember that each carbon atom in the compound contributes 1.1% to the height of the M+1 peak. So if we're trying to figure out how many carbon atoms we have, we're going to take 4.4% and divide it by 1.1%, and what we get is 4. That means our molecule has 4 carbon atoms. All right, so that's the strategy when we're given our molecular ion peak and our M+1 peak, and we're given the percents, and we want to figure out the number of carbon atoms. We divide the relative percents, the relative height percents of each. All right, and then we take this final percent and divide it by 1.1. And the number we get is the number of carbon atoms we have. All right, so we have 4 carbon atoms. All right, and carbon atoms have a molecular weight of 12. All right, that's going to give us 48. All right, but our molecule has a total molecular weight of 72. We're given the molecular ion weight. Your molecular ion weight is the total weight of your molecule, 72. All right, all the carbon atoms make up a total of 48. So let's take 72 minus 48. We have 24 AMUs to account for. All right, they can't all be hydrogens, so there has to be something else. All right, it can't be nitrogen because that would usually give us an odd molecular weight. 72 is an even number. So we can potentially have, for example, maybe an oxygen atom here. An oxygen atom has 16 AMUs. So if we subtract 16 from that, then we have a total of 8 left. All right, that makes sense to have 8 total hydrogens. All right, so if we're trying to propose one molecular formula for what this could be, we can say this: C4H8O. All right, so this can be our proposed molecular formula for the information that we have been given. Fantastic. All right, let's move on to this next problem. This next problem says, below are mass spectra for 4 different compounds. Identify if these compounds contain bromine, chlorine, or neither. Well, if we look at this first molecular spectra, all right, looking here at the end where we can potentially have our molecular ion peak, all right, there is no significant M+2 peak here. So we really can't say we have a chlorine or bromine atom. So we're going to say neither. Same here, if we look near the end where our molecular ion peak will usually be, we don't see a M+2 peak. So again, we can't say that there is a chlorine or a bromine. Now, if we look at C, we have our molecular ion peak right here, and we have an M+2 right there. And guess what? They are equivalent in height. The molecular ion peak, and I'm going to zoom in here, all right, this molecular ion peak M plus and this M plus 2 peak, all right, are equal in height. All right, that means that what is present here is a bromine. Now, if we look at D, all right, we have our molecular ion peak, and then we have an M plus 2, and they are about, the M plus 2 is about 1/3 of the molecular ion peak. That means what we have here is a chlorine atom that is present in our compound. Fantastic. All right, now let's look at a few more things that are going to help us determine and extract a little bit more information from our mass spectra. We're going to look at trends that are going to help us know when we have certain fragments of alkanes, when we have alcohol fragments, amine fragments, or carbonyls. And we have discussed that how the majority of the peaks in our mass spectrum are produced from fragmentations of the molecular ion. Now, if we look at pentane right here, this example we have, if we look at pentane, we can observe some of the common fragmentations of alkanes. We see here the molecular ion of pentane. All right, this is the molecular ion of pentane. All right, and we can see that peak right here. This is the molecular ion peak for pentane. It's obviously not the base peak here. Here's the base peak right there. All right, but our molecular ion peak is right here. Fantastic. Now, when pentane fragments in a way where it looks like a methyl group has been lost, all right, right here, our pentane has lost a methyl group, okay, we call that peak M minus 15 because 15 is the mass of the methyl group that is fragmented off. And so the new molecular mass of this 4-carbon chain right here is whatever the weight of pentane subtracted by 15. All right, and we see this peak right here. All right, whenever pentane loses a methyl group, all right, the methyl group has a weight of 15, all right, pentane's weight minus 15, all right, it gets that peak. That peak is this group right here. All right, and this is the same logic for all the other possible fragmentations we see in this mass spectra. If pentane lost an ethyl group, all right, if it lost an ethyl group, all right, an ethyl group has a weight of 29, all right, so the molecular weight of pentane minus 29 gives the molecular weight of this carbon fragment right here, and this peak is seen right there. Now, you might ask, well, I see all the fragments that are in the image in the mass spectra. What are the smaller peaks surrounding M minus 15, M minus 29, M minus 43? What are all these smaller fragments that surround each of these bigger fragments that we've talked about? Well, these smaller peaks surrounding are related to the loss of hydrogens in addition. All right, so in addition to that, some common fragment patterns that you should be aware of for alcohols. Well, alcohols can fragment in two ways: alpha cleavage and dehydration. What is important to remember is that a signal at molecular weight minus 18, M minus 18, is a characteristic of an alcohol group, the loss of water from an alcohol. Amines, they fragment through alpha cleavage, and you know that nitrogen is present in your molecule when the molecular weight of the parent ion is odd. Ketones and aldehydes undergo something called Mclafferty Rearrangement. I can never pronounce that. That results in the loss of a neutral alkene, and a signal at M minus X, where X is an even number, all right, is a characteristic of this rearrangement. This table of common fragments in mass spectrometry is very important. All right, when you identify your molecular ion peak, all right, and then you see a peak at at M minus 15, where M is your molecular ion fragment, all right, if it's say at 72, for example, all right, if you see another peak at 72 minus 15, all right, which should be like 58, I think. No, that's wrong. 72 minus 15 should give you 57. Okay, that seems more right. Yeah. All right. If you see another peak at 57, then what you can conclude, all right, you have a peak at 72. That's your molecular ion peak. All right. If you see 72 minus 15, so another peak at 57, what you can tell is this peak is your molecular ion that has lost a methyl radical. All right, if you see a peak at M minus 29, then that's an ethyl radical that has been lost from your original molecular ion. M minus 43 is the loss of a propyl radical. M minus 57 is the loss of a butyl radical, right? M minus 18 is the loss of a water from an alcohol. And M minus X, where X is an even number, signals this rearrangement for ketones and aldehydes. Now, again, this is best understood by doing some practice problems. So let's go ahead and jump into a few practice problems so we can really understand. All right, so this problem says the sex attractant of the codling moth gives an IR spectrum with a broad signal between 32 and 3600 centimeters inverse and two signals between 16 and 1700 centimeters inverse. In the mass spectrum of this compound, the molecular ion peak appears at 196, and the relative abundance of the molecular ion and the M+1 peak are 27.2% and 3.9% respectively. A asks us, what are the functional groups that are present in this compound? Well, right, we have to remember our infrared spectroscopy. A peak between 3200 and 3600 centimeters inverse is distinct to an alcohol group, and having a peak between 16 and 1700 centimeters inverse signals the presence of a carbonyl and a double bond. All right, so our carbonyl. Fantastic. So that answers the first question. Now, the second question asks us, well, how many carbon atoms are present in the compound? Well, what we have to do, all right, we have our molecular ion. Its relative height to the base peak is 27.2%. We have our M+1 peak. Its relative height to the base peak is 3.9%. You know what we have to do? We have to divide 3.9% by 27.2% and multiply that by 100% to get about 14.3%. Now, we're not done. We have to take the 14.3% and divide it by 1.1%, and what we get is approximately 13. That means our molecule has about 13 carbon atoms. Now, 13 carbon atoms multiplied by 12 gives us about 172. But our total molecular weight is 196. So if we take 196 and we subtract it by 172, that's going to give us 424. All right, 24. Remember, though, we have an oxygen, right? Because we concluded that we have a carbonyl atom from the signal in our IR spectra. All right, so we also have one oxygen atom, so we have to subtract 16 from this. All right, that leaves us 8. So we have one oxygen atom, 13 carbon atoms, and the rest of these 8 are probably hydrogen atoms. So for C, based on the information, we want to propose a molecular formula for this compound. Well, we can propose 13 carbon atoms, 8 hydrogen atoms, and 1 oxygen. So that's how we use all this information to help us conclude and help us propose a molecular formula for the compound based on all this information that they have provided for us. Now, this question says, the following are an IR spectra and a mass spectra for an unknown compound. Propose at least 2 possible structures for the unknown compound. Fantastic. So we have to propose 2 possible structures. Let's start by looking at the IR. We have the strong peak around 1720. This relates to a carbonyl. All right, so looking at the IR spectra, we can tell we have a carbonyl, and we can tell, right, this is sp3 carbon to hydrogen. All right, so we can go ahead and write that we have carbon binded to hydrogen as sp3. All right, fantastic. That's what we can conclude easily from this IR spectrum. Now, let's look at our mass spectrum. All right, here is our molecular ion peak. All right, we can tell it's right here. It's at about 86, because this is 85 and then it's one more, so 86. This is our molecular ion peak. It's at 86. It has a molecular weight of 86. Well, what we can quickly notice, all right, is that we have a peak at M minus 43. All right, molecular weight minus 43. So that would be 86 minus 43. We have a peak at 43. Look at this big peak at 43. That's M minus 43 peak. What do we know about an M minus 43 peak? Well, if we go ahead and go all the way back up here and look at the common fragments in mass spectrometry, M minus 43 is the loss of a propyl radical. All right. So we know that our molecular weight is at 86, and we know that this M minus 43 peak refers to the loss of a propyl group. All right. That means that it could look like, this loss of a propyl group can look like this, right? A 3-carbon chain, or it can look something like, and it's binded to something else, this R group to the rest of it, or it can look something like this. All right, this is still a propyl group with 3 carbons. All right, so now if we're trying to propose 2 possible structures for this unknown compound, we know it has a carbonyl group. We know that it has to have some propyl group because it loses that propyl group when it is fragmented. What we can draw as 2 potential structures can look like this. All right, or like this, for example. Now we can double check this by making sure, all right, that they have, these 2 proposed molecules have the molecular weight that we have identified for our molecular ion. So here we've drawn 1, 2, 3, 4, 5 carbon structure. So there's 5 carbons in both of these. 5 times 12 is 60. Fantastic. Is 60. All right. We have an oxygen atom that's 16. So that leads us to 76. All right. And then we should have about 10 hydrogens to give us to 86. And there are actually 10 hydrogens here. Here's 3, 5, 7, and 10. All right. So that was a way that we put together our carbonyl group, all right, and our propyl fragments that we know are there in our molecular structure, and we put it together to make sure that the proposed structures we give make sense. All right, fantastic. Now let's do this next problem. Now this next problem says a novel molecule was isolated from a native Texas plant by one of Dr. Lovely's research students. All right, this problem is from an old exam I had. The student obtained, and Dr. Lovely was the professor, the student obtained the mass spectrum of the compound and determined that the molecular formula was C17H21, bromine, chlorine, nitrogen, and 6 oxygen. How many degrees of unsaturation does this compound contain? All right, so we haven't talked about figuring out the degree of unsaturation. There's a formula for this, and I wanted to talk about it when we're doing a practice problem. But essentially, when it's asking us for the degree of unsaturation, this is another way of asking for the presence of double and triple bonds. How many triple or double bonds are there in this molecule potentially? All right, so the formula for degrees of unsaturation is this hydrogen degree index formula, and it is 1/2 2 times the number of carbons you have, all right, plus 2 plus the number of nitrogens you have minus the number of hydrogens you have minus the number of halogens you have. All right, so here we have 1/2 2 times the number of carbons we have. We have 17 carbons plus 2 plus the number of nitrogens we have. We only have 1 nitrogen here minus the number of hydrogens we have. We have 21 hydrogens minus the number of halogens. We have a bromine and a chlorine, so we have 2 halogens. Now, if we calculate all of this, if we throw this in the calculator, we're going to get 7. So the number of the number of degrees of unsaturation this compound has is 7. Fantastic. Let's do this next problem. The so-called nitrogen rule states that a compound with an odd number of nitrogens should exhibit what? Well, we've talked about this, the nitrogen rule. If you have an odd value for your molecular weight, then you're going to have an odd number of nitrogens. So the answer to this is B. This question asks, which of the following spectra are consistent with a molecule that contains a bromine? All right, remember a bromine is going to have, it's going to have your molecular ion peak, and it's going to have a M+2 peak. All right, and they're going to have the same relative height for their peaks. All right, so if we want to identify a spectra where your molecular ion peak and your M+2 peak, all right, have the same relative height, all right, look at this. B has your molecular ion and an M+2 peak that are the same relative height. B is the answer. Now, if you look at A, all right, here's your molecular ion peak, very small. There's no M+2 peak next to it that is the same relative height. So it couldn't have been that. Let's look at C. Here's our molecular ion. All right. There's no M+2 peak there. And here's our molecular ion in this spectra, and we don't see an M+2 peak, and we don't even see one that's the same height. So that's how we concluded that. Now, this problem says, aside from carbon and hydrogen, what other element is present in the molecule? Well, let's look at the spectra. All right, here's our molecular ion peak. All right, and right next to it at an M+2, here's the M+2 peak. It has an M+2 peak. How exciting is that? The M+2 peak is about 1/3 of the molecular ion peak. All right, this is indicative of a chlorine atom present. All right, whenever you have a molecular ion peak and there's an M+2 peak, all right, you're thinking either chlorine or bromine. How can you tell if it's chlorine or bromine? Well, bromine is going to have the M and the M+2 be equal height, whereas the chlorine, the M+2 peak is going to be 1/3 of the molecular ion peak. And we see that here, the M+2 peak is 1/3 of the molecular ion peak. So we know that there is a chlorine atom present in this molecule. Fantastic. Those are all the practice problems we have. I hope this was helpful. If you have any questions at all, leave them in the comments or email me. If you want to see more practice problem for this chapter in general, send me practice problems that you would want to see in a problem set video. Other than that, good luck, happy studying, and have a great day.